Welcome back, everybody. Today we'll be looking at another curvilinear problem dealing with polar coordinates. So the problem states rod OA rotates counterclockwise with a constant angular velocity of 5 radians per second. The double collar B is pin connected together such that one collar slides over the rotating rod and the other slides over the horizontal curved rod, of which the shape is described by the equation R. If both collars weigh 0.75 pounds, determine the normal force which the curved rod exerts on one collar at the instant theta equals 120 degrees, and we can neglect friction. So when I was actually solving this problem, I was actually getting the problem wrong because I misread the problem. So let me point out that error there because it might be unclear. So when you see this diagram, you might think this mechanism is in the vertical direction. So what I'm saying is that the weight of these components are being directed downward. But actually it isn't. And that's because of this word right here, which I didn't notice for the longest time. This word horizontal curved rod. So what that means, let's imagine a table somewhere. So this is a table like that. And this mechanism is actually on the table. So if we draw box right here and then another box over here, the mechanism is going like that, where gravity is pointing in this downward direction, not this way, as this diagram would look like if it was in the vertical direction. So this purple arrow is the same as if it was pointing in that direction. And that's not how gravity works. Gravity points directly downward, so it'll be in that direction because it is a horizontal curved rod. So therefore this vector of the weight actually points away from you into the screen. So like that. If that's the end of the vector, it's actually pointing into the screen. And that might actually be a little confusing because they do give you the weight. And later on we'll see that the weight does not actually matter. They try to trick you with horizontal curved rod and the weight. So that's one thing to point out, which I'm kind of embarrassed of how long that took me to figure out. But that's probably where most problems occur, to be honest. So whenever you see horizontal somewhere, that probably indicates that this mechanism is not in the vertical direction such that gravity acts this way. It actually points either towards you or away from you. And another thing to point out is this double collar. So this might be a little confusing for some people because they don't know what a double collar is. Okay, so let me redraw this component of the diagram. This double collar, this first collar in the foreground, is actually not connected to the rod itself. It slides with the rod. So this is what it might look like in a three-dimensional view. And this is where the rod actually exists, the rod OA. And as the double collar moves along the path, this collar in the foreground slides up and down the rod OA. While in the background, this collar over here is sliding in this direction and along the path that R describes. And one thing to point out is that these right here, these angles between them, does not mean it is perpendicular to each other. So I'm saying that this collar in the foreground is not perpendicular to the one in the background. It can be, but in the most general case, that is not true. So when we solve this problem, we have to make sure that this angle is in the general case, meaning it's not perpendicular to it. Okay, with that being said, we could actually start with the problem. Okay, since we're gonna try to find the normal force of this diagram of one of the collars, we're gonna have to find acceleration of the collar. So that's the thing I'm going to do. I'm going to use this equation to find the acceleration. So to generalize this problem a little bit more, these constants in the equations are fairly random, so I'm going to define them as alpha and beta, just to generalize the problem so we don't have to deal with numerical calculations on the way. So to find the acceleration, we're going to have to take time derivatives. So the first time derivative is going to be beta sine of theta, and then we have to do the chain rule, so that's going to be theta dot. So if we plug in the value of theta when it equals 120 degrees, this is going to be 6.495 feet per second. And as well, we're going to need the position later, so we're going to plug in the value for r of theta equals 120 degrees. And that's simply going to equal 3.75 feet. Now to find the acceleration in the radial direction, all we have to do is take another time derivative of this equation. I actually forgot a negative here. I'm sorry, this should be a negative beta. So we're going to pull out that negative beta and then do the product rule as well as the chain rule. So derivative of sine is cosine of theta. Then we have to do the chain rule. So that's going to be theta dot. And then we multiply by theta dot again. So that's going to be another theta dot. Then we're going to add the derivative of theta dot. So that's going to be theta double dot times the sine of theta. And this value right here is going to be 0 because in the problem it said that it's rotating with constant angular velocity. So therefore there's no acceleration in the angular direction. So therefore this whole term goes away. So from this equation, if we plug in the value of theta dot and theta, well, we're going to get 120 and then 5 radians per second. And that ends up being 18.75 feet per second squared. So all these values that we found when theta equals 120 degrees are going to be useful later when we plug into our equations of acceleration that we derived earlier. So now we're going to do some geometry. So we're going to have the pin. I'm going to just denote this geometry in terms of the pin because that's where the axis of the rod actually goes through. So I'm not going to look at the collars because it can just be modeled by just a particle. So this, in terms of, very basic shapes, this is actually the rod OA, and this is going to be the horizontal line at which the angle theta is being measured. So we could say that this right here is theta. So this is going to be the tangent line of the curved rod, and that doesn't have to be perpendicular to the rod OA. And then I'm going to define the perpendicular line to the tangent line. So that'll look something like this. So the reason why I'm doing this is because we're going to need to know some angles over here to do the force analysis later. And as we derived earlier and try to understand more completely, we can define the angle between the radial vector, which is rod OA, and the tangent line by looking at the magnitude of r with its derivative with respect to theta. So if you remember the equation, tangent phi is simply r divided by dr d theta. So you might be asking, what angle is phi? Is it actually this angle right here, or is it this angle right here? And that's a good question. If you don't understand which angle this is, I recommend to go check out my video that I made that describes how to find this angle phi. In a very simple sense, you could find this angle by looking at this radial vector and the tangent line and the angle that is left to it, which is phi, as it sweeps around this circle in this direction. So since the concavity is like this, that is like this side of the circle, so you could say that this angle right here is phi. That's a very simple case. If you don't understand why this is true, again, go check out my video. I try to explain it as best as I can so that you don't get confused on which angle to choose. So therefore, this angle right here is going to be phi. And then later on, I'm going to define this angle as epsilon. And since this line is perpendicular to this tangent line, we could say that these two angles add up to 90 degrees. So we could say that epsilon plus phi is simply 90 degrees. Okay, before we move on, let's relate this angle theta to this point over here. So what we can do is actually draw a vertical line directly downward and then a horizontal line directly to the left of it. So I'm just extending lines and creating vertical lines so that we can create a right triangle. So this is going to be a right triangle. So this is going to be 180 minus theta. Theta minus 90 degrees. And I believe we need this angle later on. I assume it is. I don't know if we do need it, but I think we do. So now that we have all that, what we can do is use this equation to find theta. So we defined r as alpha plus beta cosine of theta. So the derivative of r with respect to theta is simply negative b sine of theta, or negative beta times the sine of theta. So if you evaluate this when theta equals 120 degrees, that's going to be negative 1.5 times the sine of 120 degrees. So that's going to be dr d theta. Theta equals 120 is simply going to be 1.299. So if we solve for phi, we could say that phi is simply the tan inverse of 3.75, that is r when theta equals 120 degrees, divided by 1.299, and that's going to give you an angle of 70.894 degrees. And then by using the equation epsilon plus phi equals 90 degrees, that implies that epsilon is 19.106 degrees. So we're going to need these angles later on to use our force analysis equations. So the next thing we're going to do is actually find the acceleration of that double collar in terms of theta, the angular velocity, and angular acceleration, although there is no angular acceleration. So in the previous video, we derived an equation for acceleration in terms of radial and theta components. So if you don't know where this equation comes from, please check my video on the derivation. So we define that the acceleration vector is defined by r double dot minus r theta dot squared. And all that is in the radial direction plus 2r dot theta dot plus r theta double dot. And this is going to be in the theta direction, or the rotational direction. Since we're rotating at constant angular velocity, this value right here is 0. So all we have to do is plug in these values which we found earlier to find the acceleration vector. Before we do that though, let me tell you the direction of ER and E theta. So ER goes along the radial direction, so therefore I'm going to call this direction right here. So I'm going to move that over here. That direction, this line is parallel to the rod. This is going to be ER. And then E theta is going to be along the direction of movement, or at which the angle rotates. So this is going to be E theta. And these vectors are perpendicular to each other, but do not confuse E theta with the tangent line of the background collar. So I'm saying if you drew a tangent line to the curved rod, that direction of the tangent line does not have to be in the direction of E theta. It can be, but we do not know that, so we have to assume that it isn't. And that's why we found those different angles earlier. And we proved that it isn't because we found the angle phi, which is not 90 degrees. So therefore E theta does not actually point in the tangent direction of the curved rod. However, E theta is perpendicular to the rod or the radial vector. So I just wanted to clear that up. So I'm going to plug in the values. So A is... So this is the acceleration vector. After plugging in all those values, this is the acceleration vector when theta equals 120 degrees. So at the instant when theta equals 120 degrees, the acceleration is defined by this vector. So this is going to be the free body diagram of both the collars. So all these lines intersect at the pin between those two collars. So that's where all the normal forces are going to interact, right at the pin. So since this foreground collar has a rod going through it, that means there's a normal force between the rod and the collar. And that's going to be perpendicular to the collar. So that means that that normal force is going to look something like this, where this vector is perpendicular to the axis rod. And then similarly, there's going to be another normal vector on the other collar with respect to the curved rod. Therefore, there's going to be a normal force acting in this direction, which is along the green line, which is perpendicular to the tangent to the curved rod. So this is going to be N2. Now you may be asking, what about the weight? Again, this mechanism is actually on a table, so let me draw that out again. So if we have a table, the mechanism is actually on the table, so the weight force is actually pointing directly downward. And in this diagram, that would mean that the weight force will be pointing directly at you or directly away from you, depending on how the mechanism is oriented by the picture that was given to us. So what that means is that the weight force does not affect this problem because it is not within the plane that we're looking at in this problem. It directly passes through the plane, so we could ignore it. So since I thought this picture was a little cluttered, this is the vector diagram without all the extra stuff. So now that we have that, we're just going to sum the forces in the ER direction and in the E theta direction. So if we sum the forces in the radial direction, and I'm going to define this direction positive, which is in the direction of ER. So in this direction, I'm going to define as positive. So this is going to equal minus N2 cosine of epsilon. So that's this component right here. And since N1 is perpendicular to the axis of the rod, it is also perpendicular to ER. Therefore, there is no component of N1 in this equation. So this right here is perpendicular, so that means there's no component of N1 in the radial direction. And that's going to equal the mass times the acceleration in the radial direction. So if we solve for N2, that's simply going to be negative m times the acceleration in the radial direction divided by the cosine of epsilon. So if we plug in those values, so we're going to get negative, and we're going to look at only the first collar, or the collar in the foreground, because that is where N2 is being applied. So therefore, we don't have to include the weight of the collar in the background. So that's going to be 0.75 divided by 32.2 feet per second squared. So this is just units of slugs. And we're going to put the acceleration in the radial direction. So that's going to be, as we found earlier, negative 112.5. So this is going to be negative 112.5. And you might be asking, why is the acceleration negative? So our vector had a negative ER component, so therefore the net acceleration will be pointing downward, and that is in the opposite orientation of what we defined as positive. So therefore we have to include that negative. So that's why that is negative. And then we finally divide by the cosine of that angle, which is 19.106. So therefore, N2 is simply 2.773 pounds. And to find the normal force in the other direction, all we have to do is sum the forces in the E theta direction. So if we sum the forces in the E theta direction, we're going to define this direction as positive, which is consistent with our diagram. So that's going to equal N1 plus N2 sine of epsilon. And that's going to equal the mass times acceleration in the theta direction. So the reason why N1 is fully in the E theta direction, that is because of this right here. N1 is perpendicular to the radial axis, and as we said earlier, ER and E theta are perpendicular to each other. So therefore, N1 strictly lives in the direction of E theta. And that's how we defined our equation. N2 sine of epsilon is simply this force vector right here. So we just use some trigonometry to find that component. And to find N1, all you have to do is subtract N2 sine epsilon on both sides. So that'll be MA theta minus N2 sine of epsilon. So that equals 0.75 divided by 32.2. And again, the reason why we're only looking at 0.75 is because we're only looking at the background collar, not both collars at once. And the acceleration in the theta direction is going to be 64.95, and that is in the direction that is signified here, so it is not negative. And then we're going to subtract N2, so that's going to be 2.773 times the sine of epsilon, so that's going to be 19.106. And if you plug in all these values for N1, you get 0.605 pounds. So hopefully that wasn't too confusing. I'm going to quickly recap on what we just did. So the first thing we did was recognize that this is a horizontal curved rod, meaning gravity is pointing directly at you or away from you, depending on this orientation of the picture. Then we defined what a double collar is, and we said that the angle between these two collars does not have to be perpendicular to each other. They could look something like this, where this angle right here is not 90 degrees. So these two collars can point in any arbitrary direction that is dependent on how the rod is and how this curved rod is. Since our goal is to find the normal forces, the next step is actually to find acceleration so we can relate that to Newton's second law. So we were given an equation of r with respect to theta, and we took time derivatives of this to find the acceleration. And then we also plugged in the values for r and r dot when the angle is 120 degrees, because we're going to need this later to plug into our acceleration formula. Next, we define the geometry of the problem, such as the angle between the tangent line and the axis of the rod, or the radial direction. So we need this angle to define the normal vectors that are acting on the double collar. And we use the equation tangent phi and this epsilon plus phi to get these two angles. And if you're confused on why this angle is phi and not this angle right here, then please go check my video on that. I I explained it in detail, and hopefully you understand why this is phi. So we use those equations to find phi and epsilon. Then we use the equation of acceleration in the ER and E theta directions. If you don't know where this equation comes from, please check out my video on the derivation of this. It's probably best for you to memorize this. You can derive it if you want, but it's probably best for you to memorize this so you can quickly just plug in numbers to get the acceleration vector. So when we did plug in the numbers, we got this acceleration vector when theta is 120 degrees. So I drew out the free body diagram of the two collars, and there's going to be a normal force acting on the background collar that is perpendicular to the tangent line. And that's simply because the curved rod is within the axis of the collar in the background. So therefore, the normal force can act perpendicularly to the curved rod and the collar itself. And likewise, there's going to be another normal force on the collar in the foreground that is perpendicular to the rod and the collar. So those are the two vectors of forces that are acting on the collar. And again, you might be asking, what about weight? The weight does not matter in this problem because you could imagine that this mechanism is on a table. Therefore, the weight vector points directly downward, or in this diagram, the weight vector points at you or away from you, depending on the orientation of this mechanism. So therefore, there's only these two forces in this diagram. And you can see that a little bit easier in this diagram right here. So we defined our orientation in this direction, ER and E theta, and we use these directions to develop the equation for Newton's second law. So we said that the sum of the forces in the radial direction is positive in that direction. So then we just broke up the components of N2 and found N2 in the radial direction. And we could say N1 is perpendicular to the radial direction because the normal force acts perpendicularly to the contact surface. So there's no component of N1 in the radial direction. So therefore, there's only this component of N2 in the radial direction. And that's going to equal the mass times the acceleration in the radial direction, which we found by that acceleration vector equation. And you might be wondering why AR is negative, and that's because the vector equation told us that the acceleration in the radial direction was negative, meaning it points in the opposite direction of ER, so that would be in this direction. So since the acceleration AR points in that direction, it is in the opposite direction that we defined earlier, so therefore we have to say that it is negative. So then we plug in the values for mass, and again, remember that we're in the US customary unit, so we have to use slugs. So we divide by the gravity, which is 32.2 feet per second squared, and the weight is in pounds. And then we get a value for N2, which is 2.773 pounds. And we repeated the process in the theta direction and said this is the positive direction. So again, this is E theta, and this is ER. And we got this equation, and all we did was solve for N1 by subtracting this on both sides of the equation, plugged in some numbers, and what we got was N1 equals 0.605 pounds. So again, the hardest thing about this problem was the tricks that were in the problem. Noticing that it was a horizontal curve was one thing that took me so long to figure out, and realize that the weight vector does not actually affect this problem. And also another thing that is kind of tricky is understanding how a double collar pin works and recognizing that the angle between the two collars does not have to be perpendicular to each other. Those are probably the two tricky things that you have to keep in mind, as well as when you take the derivative with respect to timing, you have to do the product rule as well as the chain rule. So there's a lot of little errors that you can make on the way, so you have to be very meticulous and cautious when you solve this problem. In essence, I always recommend you just to think of the most general case of the problem. Don't assume any angles unless the math tells you the angle is so-called those perfect angles such as 45 degrees, 30 degrees, 60 degrees, or 90 degrees, so forth. Don't assume those angles unless the math tells you they are those angles. So with that being said, I'll see you in the next video.